Good morning, everyone. Today I will introduce a research paper by Jason and his colleagues, which developed a deep reinforcement learning framework to optimize the urban land use for carbon emission reduction. This work is a collaboration between multiple institutions, including the University of Nottingham, China, and the University of Harvard. Points out that rapid urbanizations has led to soaring carbon emissions. Traditional planning methods are static and cannot adapt to dynamic city systems, while existing AI models can predict emissions. They cannot generate actionable spatial strategies through sequential decision-making. This creates a critical research gap that the study aims to fill. Three main objectives. First, to develop a DRM framework that integrates multi-source urban data. Second, to clarify the agent's spatial strategies and emission reductions. And third, to provide evidence-based insights for sustainable urban policy development. The authors collect three types of data: points of interest from Google Map, areas of interest from land parcel data, and the transportation network from OpenStreetMap. The study area in Hangzhou was divided into a 42 by 32 grid, with each kill measuring 500 by 500 meters. They use the Proximo's policies optimization algorithm to train agents that adjust the land use approximations to minimize carbon emissions. This is the source from the Google Map, and this is the source from the OpenStreetMap. In their model, total emissions consist of two parts: base emissions from land use and path emissions from transportations. Base emissions are calculated using emission factor for each land use type, such as 28.5 km per square meter for residential areas. Path emissions are estimated using a discrete virtual model that considers model probabilities and travel distance. The reward expression is the reductions in total normalization emissions after each. Just like Hangzhou's central area as their case study, after 400 training episodes, the model converged with stable losses. The research shows an average emission reduction of 15%, with the best episodes reaching nearly 19%. Their strategy centralized daily life functioning like residential, dining, and shopping area into compact mixed-use configurations. Educational and medical functions, however, remained more dispersed, relying on the transportation network for accessibilities. The gaming conflicts trend converted increasing concentrations over time. Authors compared PPO with genetic algorithms and linear regressions. PPO achieved 15% emissions reductions, significantly outperformed the genetic algorithms at 16%. Several limitations. The environment is deterministic, ignoring real-world uncertainties. The optimizations focus only on carbon, not on social or economic factors, and the results are specific to Hangzhou. Future work proposed by authors will incorporate multi-objectives optimizations, test other cities, and use dynamic emission factor to improve realism. Thank you for listening.